This is a quick and dirty introduction into the two main types of statistics that we use today, frequentist and Bayesian statistics. And also, I shall cover why we are using Bayesian statistics as part of the Stoc project. The Stoc project is a pan-European project to look at how best to develop tools to estimate the probability that a herd is free of disease. The frequentist or traditional approach to statistics starts off with a null hypothesis, and then we take data and we work out how unlikely those data would be had the null hypothesis been true. And if we decide that it would be very unlikely to get such data, then we go back and we reject the null hypothesis and choose the alternative to that. Bayesian, which is a more recent development in statistics, involves creating a model with parameters. That's variables that can take different values, and we then consider what values in advance we think that those parameters should take. And we don't just consider a single value, we consider a range and so uncertainty. We bring in the data, and then once we run our Bayesian model, we are then in a position to estimate the different parameter values or the different values for all the different parameters in the model that seem likely given the data. I'm now going to talk about a very simple example. It's overly simple, but it's useful just to demonstrate the difference between the two types of statistics. So imagine that we've got a coin and we're considering whether the coin tosses fair, whether it is 50-50 heads and tails or whether it's something other than that. So with the frequentist approach, our null hypothesis is that it is fair, that it's a 50-50 chance that heads will come up. And we bring in some data, we toss the coin several times, and these are the data that we get. You can see that there's a domination by heads there, which looks a bit unlikely. So the frequentist approach is to say, how likely would it be to get such data if indeed the coin was fair? And we end up with a probability, and that probability is our famous p-value. And if the p-value is small, as it is in this case, then we think that it's unlikely that the null hypothesis was true, given that it's unlikely to get such data if the null hypothesis were true. And so we reject that null hypothesis and decide that the coin is unfair. If, on the other hand, we take the Bayesian approach, we have a parameter, and the parameter is the fairness of the coin. It's not that we're constructing two alternative hypotheses. We've got a model in which we've got a parameter, and that parameter is the fairness of the coin. So it basically is the probability that the coin will come up heads. So it ranges from 0 to 1. We then put our data in, and we then get what we see in the bottom of this graph, or the bottom of this slide, which is a large number of simulations of what we think are the most likely values for the probability of the coin coming up heads. And as you can see, we've not just got a single estimate, we've got a lot of different estimates, and we've got a range. And we can calculate what's called the 95% credible interval, which is equivalent to a confidence interval, roughly equivalent, which says that 95% of our simulations or our estimates lie within that range. So what does Bayesian bring to the Stoc project? Well, let's consider the disadvantages of the Bayesian approach. First of all, it does involve a lot of simulation. The example that I gave previously was very simple and actually doesn't need fancy computing to calculate a Bayesian interval or a Bayesian estimate. But most models become much more complicated than that, and they involve various parameters, each of which can have their own values, and so we require a lot of computing power. But that doesn't matter now because we've got good computing power. The Bayesian approach depends on choosing our prior, so deciding what we consider to be the most likely distribution of the values of the parameters, and then feeding that into the model before we even feed in the data. And sometimes the output, the distribution we get at the end, the posterior distribution, can be sensitive to those choices of priors. On the other hand, actually being able to feed in prior information is also a useful thing in itself. The other possible disadvantage of the Bayesian approach is that rather than giving a single point estimate, it gives a large number of simulations or a large number of values for our parameters. But actually that's more realistic because we know that the world is uncertain. So expressing that uncertainty in the form of a distribution is totally reasonable. The advantages of the Bayesian approach. Well, first of all, I would say it's probably more relevant to humans. We normally would like to know what the data mean rather than how unlikely the data were given a particular hypothesis, which is the frequentist approach. But probably more importantly, is that it's incredibly flexible. It's much more flexible than the frequentist approach. The assumptions that are required are less strict, and so we can almost construct any statistical model that we can think of. And in the stock-free environment, that flexibility is important. In fact, the flexibility of the Bayesian approach is so good that we can include variables in the model that we can't directly measure. So these are called latent variables, and it might be, for example, that we cannot measure directly the status of a herd, and that is the case for most diseases because most tests are not perfect. So the true status of the herd is effectively a latent variable, but it's something that we can get an estimate of because of the flexibility of the Bayesian approach. And then another advantage of the Bayesian approach is that as we get new data, even if those data are of a slightly different form, we can fairly easily improve our estimates. We can update our estimates. And another benefit or advantage of the Bayesian approach is that data can be incorporated in different ways. So we can actually use data that are slightly different to as part of the same process. So coming to stock-free, why is Bayesian so important for the stock-free project? Well, the stock-free project aims to get a good estimate of the probability that a herd is free of disease. And our primary example disease for this purpose, for the first stage in this project, is BVD. Now, we already know that in epidemiology, that there are various parameters that feed into the probability that a herd is free of disease. So some of these are latent variables. So there's the probability that we get a false positive or a false negative when we test a herd. There's also the actual status of the herd, which isn't directly observed. So I hope that you can see that for stock-free, having the flexibility to have these latent variables means that really, without showing you the maths, not only is the Bayesian approach useful, it was necessary. And finally, the other advantage of the another advantage of the Bayesian approach to the stock-free project is that the stock-free project is across the whole of Europe, and in different countries, we're collecting data in different ways. And the Bayesian method has the flexibility to incorporate data collected in different ways. And so it's because we've had access to the computing power and the flexibility of the Bayesian approach that the stock-free project has already progressed very well and has produced useful and interesting results as published earlier this year.